500 tons of timber, hand-cut, hand-hauled, hand-shaped into a ship that would face the North Pacific's worst. In 1930, this is how it was done. Axes, crosscut saws, horses, steam, muscle, sweat, blood. It was brutal. It was slow. Men died doing it. But it worked. And for more than 150 years, this was the only way America built ships from trees. This isn't about one machine. This is about the last generation of men who turned forests into fleets, using methods their great-grandfathers would recognize. It's about a supply chain that stretched from mountain forests to coastal shipyards, across thousands of miles, and 2 years of back-breaking labor. It's about a process so dangerous that death was just another line item in the ledger. Before we're done, you'll understand why it took 2 years to move a tree from stump to ship. You'll see the hidden cost paid in crushed bones, drowned men, and destroyed lungs. And you'll learn what finally killed this ancient trade, because it wasn't safety regulations or public outcry. This is the story of stumps, steam, and steel. The story of how America turned trees into ships in 1930, and why it all ended 20 years later. Where giants fall, Washington State, Oregon, northern Idaho. The forests here in 1930 still held timber the size of small buildings. Douglas fir, 200 feet tall, 6 feet across at the base, old enough to have been seedlings when Napoleon marched on Moscow. These trees weighed 5 to 10 tons each. They grew on mountainsides too steep for roads, in forests so dense a man could walk 20 feet and disappear. And somebody had to cut them down, drag them out, and turn them into ships. That was the job. The men who did it were timber cruisers, axemen, sawyers. They arrived at logging camps in the spring and didn't see civilization again until winter. The camps were shacks, bunkhouses, cookhouse, tool shed. 20 to 100 men living in the middle of nowhere, miles from the nearest town. No phones, mail once a week if they were lucky. They were there to harvest the impossible, because America in 1930 needed these trees, needed them for houses, for docks, for bridges, and especially for ships. Steel dominated the oceans by then, sure. The age of the great sailing ships was long dead, but thousands of wooden vessels still worked American waters. Fishing boats pulling cod and halibut out of Alaskan seas, coastal schooners hauling cargo between small ports, tugboats, barges, yachts. The Great Depression made new wooden ships attractive. They were cheaper than steel, could be built with local labor and local timber. The economics were simple. A steel fishing schooner cost $40,000 in 1930. A wooden one? $25,000. For a fisherman trying to feed his family during the Depression, that $15,000 difference was the difference between owning a boat and working someone else's deck for the rest of his life. But to build a ship, first you had to fell a forest. The process started with a scout, timber cruiser. He'd walk the forests months before the cutting crews arrived, identifying which trees to take. He looked for size, straightness, lack of rot. He marked them with an axe, a blaze cut into the bark, and mapped their locations. This wasn't guesswork. A cruiser could look at a tree and tell you within 10% how many board feet of lumber it would yield. He knew which trees had heart rot, decay that wouldn't show until you cut it down. He knew which hillsides had shallow soil that produced weak, twisted grain. He'd spend 6 months walking hundreds of miles, marking maybe 300 trees out of 10,000. The ones that didn't make the cut? They'd stand for another decade, another century, growing, waiting. When the crews arrived, they followed those marks. 2 men, 1 tree, a crosscut saw. The saw was 6 to 8 feet long, a ribbon of toothed steel with a handle at each end. It weighed maybe 20 pounds. It looked simple, it wasn't. Every tooth was hand-filed to precise angles. The cutting teeth removed wood. The raker teeth cleared the sawdust from the cut. If the angles were wrong, if one side cut faster than the other, the saw would bind, twist, jam. Filing a saw took 30 minutes and had to be done every night after work, in the dark, by lantern light, while your shoulders still burned from 10 hours of pulling. First came the undercut, a notch chopped into the downhill side of the tree with double-bit axes. 8-pound axes swung overhead, chips flying, the rhythm echoing through the forest. The undercut determined where the tree would fall. Get it wrong, and the tree went sideways, crushed equipment, killed men. The notch had to be perfect. 1/3 the diameter of the tree cut at a precise angle. Too shallow, and the tree wouldn't fall clean. Too deep, and it would snap before you wanted it to, crushing the sawyers when it kicked back. Then came the back cut, the saw. 2 men, one on each end, pulling in rhythm. Push-pull, push-pull. The teeth chewed through wood fiber, throwing sawdust with every stroke. It took 2 hours to drop a medium fir. 8 hours for a giant. Your shoulders burned, your back screamed. The saw rasped and sang, and sometimes, if you listened close, the tree started to talk. Fiber tearing deep inside, warning you it was about to go. You learned to hear it, the creak, the groan, the sharp crack that meant you had maybe 5 seconds to get clear before 10 tons of timber came down. When it fell, the ground shook. But could they actually predict where it would land? Mostly. The undercut guided it. Gravity pulled it. Wind shoved it. Experienced sawyers read the tree's lean, the canopy's weight distribution, the wind. They were right 90% of the time. The other 10%, that's when men died. Trees kicked sideways, split vertically, and exploded backward. Hung up in neighboring trees, and came down hours later without warning. Widowmakers, they called them. A branch the size of a telephone pole falling 70 feet. Silent until it hit you. Every logging camp had stories. The sawyer who called the fall wrong and took a limb through the chest. The greenhorn who didn't run fast enough when the tree barber chaired, split vertically up the trunk, and slammed backward like a spring-loaded trap. The crew that left a hung-up tree overnight and came back in the morning to find it had fallen and crushed their tool shed. You didn't talk about it much. You just worked careful, and you listened for the talk. Once the tree was down, the real work started. Limbing. Axemen swarmed the fallen giant, chopping off branches. Then came bucking, cutting the trunk into sections 16 to 40 feet long, depending on what the mill needed. Each section still weighed 1 to 4 tons. Now came the question nobody liked asking, how do you move a mountain? Because that's what these logs were, dead weight, no wheels, no motors, just mass. And they had to get from wherever the tree fell, sometimes miles into the forest, to a collection point where they could be loaded onto sleds or dumped into a river, enter the skid road, not a real road, a pathway made of logs laid perpendicular to the route, greased with animal fat or fish oil. The logs they wanted to move would be dragged over these greased rails by teams of horses or oxen. Building a skid road was its own art. You needed the right grade, gentle enough that the animals could pull the load, steep enough that gravity helped. You needed the skid logs placed at precise intervals, too far apart, and the timber sagged and bound between them, too close, and you wasted materials. And you needed grease, barrels of it, rendered animal fat from slaughterhouses, fish oil from canneries. The swampers applied it every morning with mops and brushes, coating every skid log until the whole road glistened. 4 to 8 oxen, or 2 to 6 horses, hooked to the log with chains, controlled by a teamster who walked alongside, shouting commands, cracking a whip. The animals pulled. The logs scraped over the greased skids, shedding bark and splinters. It moved maybe 100 feet before the team had to stop and rest. This went on all day, every day for months. A good team could move 6 to 8 loads a day. That's 6 to 8 logs, each one representing hours of sawing, hours of limbing and bucking. And those 6 logs, they'd traveled maybe a mile. Still had 10 more to go before they reached the landing. But what happened when the skid roads dried out? The grease wore off, friction spiked, the animals couldn't pull the load. Operation stopped. Swampers, maintenance men, had to re-grease every skid, every day. Miss one section and a multi-ton log stopped dead, blocking the entire route. And if a skid log rotted through, if it cracked under the weight, the whole road had to be rebuilt. Days lost, money lost. It was slow, it was tedious, it was the only way, unless it was winter. In the northern forests, Michigan, Wisconsin, Minnesota, winter changed everything. Snow fell, temperatures dropped below zero, and the ice road crews went to work. They'd pack down the snow on logging roads, then spray water over it at night. The water froze into a slick, glassy surface. Suddenly, the same team of horses that could pull 1 log in summer could pull 3 or 4 in winter. Sleds replaced wheels. The logs glided. The ice roads were a miracle and a nightmare. They required nightly maintenance. Every night, water had to be sprayed. Crews worked from sunset to midnight, hauling water barrels on sleds, spraying by lantern light. The water froze to their gloves, their coats, their beards. Frostbite was common. Men lost fingers, toes, noses to the cold. Every morning, the surface had to be inspected for cracks. Miss one night, and the road melted or fractured. The sleds broke through. The horses fell. The operation stopped. And if a horse broke a leg on the ice, they shot it. Right there, no vet, no rescue. The carcass was dragged off the road, and the team kept moving. This was the efficiency gain. This was the improvement. Ice roads doubled capacity and required you to work in sub-zero darkness, spraying water that froze to your clothes. But could they actually keep the roads frozen in fluctuating temperatures? Barely. Spring thaws came early some years. The roads turned to slush. Sleds sank axle deep. Entire seasons' worth of logs sat stranded, waiting for the next freeze or the next summer's dry roads. Time was money. Delays were disaster. Logging companies ran on razor-thin margins. A bad winter could bankrupt an operation. And in 1930, during the Depression, there was no credit, no loans, no second chances. You moved the timber, or you lost the camp. But if the logs made it to the collection point, if the weather held, if the animals didn't die, if the men didn't quit, then came the next impossible step. The river drive. Logs were dumped into rivers during the spring melt, thousands of them, stamped with each company's mark, a metal hammer driven into the end grain, leaving an identifying symbol. Then the water carried them downstream toward the mills. Except logs don't float in neat lines. They jam, they tangle, they pile up behind rocks and bends and create dams of timber that block entire rivers. That's where the river drivers came in. River pigs, they called themselves. Men with peavies and pike poles, long-handled tools with hooks and spikes, who walked on the floating logs, guiding them downstream, breaking up jams. They worked 12 to 16 hours a day, in ice-cold water, on logs that rolled without warning, If you slipped, you went under. If the jam broke while you were on it, thousands of tons of timber came down on your head. Most dangerous job in logging. Not one of the most dangerous. The most dangerous. How dangerous? River drivers rarely made it past age 35, drowning, crushed by logs, hypothermia. The ones who survived had scars, missing fingers, permanent limps. The ones who didn't, well, their bodies turned up downstream days later, if they turned up at all. In 1936, a log jam on Idaho's Clearwater River broke while 8 men were working it. 3 drowned. The river carried them 20 miles before search crews found them wedged under a log jam. They were buried in a town they'd never heard of, by people who didn't know their names. The worst part? The jam that killed them had been building for 3 days. Everyone knew it was dangerous. But the timber was worth money, and money was scarce. So they sent men onto the logs with pike poles, trying to break it loose before it backed up for miles. It broke loose, just not the way they wanted, but the logs kept moving, because the mill was waiting. Teeth of steam. The sawmill sat at the river's edge. Logs floated in the mill pond, a holding area where timber waited to be processed. A steam-powered crane, the pond monkey, pulled logs from the water and fed them onto the carriage. The carriage was a wheeled platform that held the log against the saw. The sawyer controlled it, making precise cuts to produce planks. The saw itself was a circular blade 4 to 6 feet in diameter, spinning at 400 to 600 revolutions per minute, powered by a steam engine. The steam engine sat in its own building, adjacent to the mill. A brick firebox, a steel boiler, a maze of pipes and valves. It consumed a ton of coal every 10 hours. Someone had to tend it constantly, shoveling coal, checking pressure gauges, bleeding steam, watching for leaks. If the boiler pressure dropped, the saw slowed down. If it climbed too high, the boiler exploded. Both happened regularly. When the saw bit into a log, the sound was deafening, a shriek of steel on wood that drowned out every other noise. Sawdust exploded into the air, a constant cloud that hung over the mill like fog. The men breathed it all day, every day. There were no masks, no ventilation systems. 70% of mill workers had hearing damage. Lung disease was universal. Most didn't live past 60, but the saw kept spinning because the planks had to be cut. The sawyer's job was to turn a round log into square-edged lumber with minimal waste. He'd make a series of parallel cuts, slabs falling away until the log became a rectangular cant, then cut that into standard dimensions, 2x4s, 2x6s, 2x8s. The off-bearers, men stationed at the saw's output side, grabbed the planks and stacked them. It required perfect timing. The sawyer had maybe 5 seconds between cuts to adjust the carriage, line up the next pass, and send the log back through. Too slow, and production fell. Too fast, and he'd make crooked cuts, waste wood, ruin the lumber. 5,000 to 10,000 board feet per 10-hour shift. That was the pace. Could the saw handle knots, hidden rot, embedded rocks? No. Knots could jam the blade. Rot weakened cuts and produced unusable lumber. Rocks, sometimes embedded decades ago by forest fires or growth around debris, could shatter teeth and send fragments flying like shrapnel. That's why the filer existed. The filer, the man who sharpened and maintained the saw, was the highest-paid worker in the mill, for good reason. A dull saw bound in the cut. A damaged tooth threw the blade off balance. At 600 RPM, even a slight wobble turned the saw into a spinning death wheel. He'd shut down the mill for 20 minutes every 4 hours. Pull the saw, examine every tooth, file the damaged ones. Heat them with a torch to temper the steel. Rehang the saw and spin it up, listening for vibrations, watching for wobbles. Blades broke. When they did, metal shrapnel tore through the mill building. Men died. In 1932, a sawmill outside of Portland lost its blade during a cut. The saw shattered, sent fragments through the roof, through the walls, killed the sawyer instantly, injured 3 others. The mill shut down for a week while they cleared the wreckage and installed a new saw. The company didn't pay for the funerals, didn't compensate the families, just hired new workers and started up again. But when it worked, when the saw was sharp, the log was clean, the sawyer was skilled, the mill could process 40 to 60 large trees in a day, enough timber to build half a ship's hull. The planks went to the lumber yard. They stacked them in the open air, separated by thin wooden strips called stickers. The stickers allowed air to circulate, drying the wood slowly. Seasoning. Green wood, freshly cut, held 40 to 60% moisture. You couldn't build a ship with it. The planks would warp, twist, split as they dried. The hull would crack. The ship would leak. Seasoning took 6 to 18 months, just sitting there, waiting. Money tied up in inventory that couldn't be sold until it was dry enough to use. For a small mill, this was crushing. You'd cut timber all summer, stack it, and then wait a year before you could sell it. Meanwhile, you still had to pay workers, maintain equipment, buy coal for the steam engine. Many mills went bankrupt during the seasoning period, couldn't make it through the waiting. Shipwrights visited the lumber yard personally. They walked between the stacks, inspecting every plank, looking for knots, splits, grain irregularities, signs of rot. They rejected 20 to 30% of the lumber. Too risky. A single bad plank installed in a hull could sink a ship. What happened to the rejected lumber? Sold cheap for construction, houses, barns, fences, or burned as waste. The shipwrights didn't care. They only wanted perfection. Because the ocean doesn't forgive mistakes, the ones that passed inspection went to the shipyard. But what were they actually building? What did a wooden ship in 1930 look like? Ribs of the Leviathan, 60 to 100 feet long, 15 to 25 feet wide. A fishing schooner, the kind that worked the Alaskan cod grounds, the halibut banks, the salmon runs. It started with the keel, the spine, a massive timber 60 to 100 feet long, 12 to 16 inches square. Straight-grained Douglas fir or white oak, no knots, no defects. This piece held the entire ship together. Finding a keel timber took months. You needed a tree tall enough, straight enough, clear enough. Most old-growth firs had some curve, some twist. The keel couldn't. It had to be dead straight, or the ship would be asymmetric from birth. When they found the right tree, they'd cut it, haul it, mill it into a square beam, and let it season for a full year. The keel couldn't warp, couldn't twist. Everything else in the ship depended on it being perfect. The keel was laid on building blocks, wooden supports that held it level. Then came the stem and stern post, the curved timbers at the bow and stern, shaped with adzes and broadaxes. Heavy cutting tools swung overhead, carving curves from straight wood. Precision work. The stem had to fit the keel at exactly the right angle, or the ship would be asymmetric, unbalanced, doomed. An experienced shipwright could shape a stem in 2 days. A novice might take a week and still get it wrong. The angle had to match the design plans exactly. Too blunt, and the ship would plow through waves instead of cutting them. Too sharp, and the bow would dig in, bury itself, capsize the vessel. Then came the frames, the ribs. This is where it got interesting, because frames had to be curved. Ships aren't rectangles. their rounded, organic shapes. The hull curves in 3 dimensions. The frames that support the planking have to match those curves. 2 options: steam-bent planks or naturally curved timber. Steam-bent was easier to find, but weaker. You'd take a straight plank, heat it in a steam box for 1 to 2 hours until the wood fibers became pliable, then clamp it to a mold and let it cool. The wood held the curve, mostly. Naturally curved timber, tree knees, compass timber, was stronger. These were trees that grew bent, shaped by wind or terrain or the weight of neighboring trees. You'd search forests for months looking for matching curves. Left side ribs and right side ribs, pairs. A 100-foot schooner needed dozens of matched pairs. Finding them took longer than building the ship. But why did naturally curved timber matter so much? Because steam-bent wood wanted to straighten. Over time, under stress, the memory of its original shape would fight the curve. Nails would loosen, frames would shift. Naturally curved timber had no memory of being straight. The curve was its original form. It stayed put. Ships built with natural frames lasted 30 years. Ships built with steam-bent frames lasted 15. The economics were brutal. A shipwright could build a schooner in 12 months with steam-bent frames, or spend 18 months searching for natural curves and then build the ship. Most customers wanted the faster option. Most shipwrights knew it was a mistake. But in 1930, during the Depression, speed mattered more than longevity. A boat that lasted 15 years was better than no boat at all, so they searched. And when they found the right trees, they cut them, hauled them, shaped them. The frames were bolted to the keel with iron drifts, long spikes driven through pre-drilled holes, spaced 18 to 24 inches apart. The skeleton took shape. Now came the skin, the planking. Planks were cut to length, then heated in the steam box, 1 to 2 hours. The wood became flexible, bendable. Workers pulled the hot plank from the box. It was scalding to touch, had to be handled with gloves and care, and clamped it to the frames. The steam box was a wooden chamber heated by a firebox underneath. You had to maintain precise temperature. Too hot, and the wood scorched, weakened, became brittle. Too cool, and it didn't bend. The firemen watched it constantly, adjusting the fire, checking the steam pressure. Each plank's edge was planed to fit tightly against the previous plank. No gaps. The fit had to be perfect, because the only thing keeping water out of a wooden ship was the tightness of the planking and the quality of the caulking. They worked from the keel upward, alternating sides to maintain symmetry. The planks were fastened with trunnels, wooden pegs, or iron spikes driven through the plank into the frame. The sound of hammers rang across the shipyard all day. But could they actually make the planks curve in 3 dimensions? Barely. The steam made wood bendable, not infinitely flexible. Sharp curves required thinner planks or multiple pieces scarfed together, overlapping joints that maintained strength while allowing the bend. The bow and stern, where the hull curves most dramatically, required the most skill. One mistake, a split, a crack, a poor fit, and that section had to be torn out and rebuilt. Time lost, money lost. A good planking crew could install 8 to 10 planks a day. A schooner hull required 300 planks. That's 30 to 40 days of work, just for the hull, and every plank had to be perfect. And they still hadn't addressed the leaks. The men with mallets caulking, the art of making a wooden ship watertight. No matter how tight the planking fit, wood moved. It swelled when wet, shrank when dry. Seasonal changes, temperature shifts, the stress of waves, all of it opened microscopic gaps between planks. Water would find those gaps. Water always found the gaps. The caulker's job was to seal them. He used oakum, tarred hemp fiber, essentially recycled rope, and drove it into the seams between planks using caulking irons and wooden mallets. The iron was a chisel-shaped tool. The caulker placed it against the seam, angled down, and struck it with the mallet. The oakum compressed into the gap. He moved the iron a few inches and struck again. Ring! Move! Ring! Move! All day, every day, for months, 3 to 4 strands per seam, pounded tight. The seam had to be filled, but not overfilled. Too much oakum and the plank would split. Too little and water would seep through. The sound of caulking was the sound of shipyards. A rhythmic ringing, iron on iron, mallet on iron, echoing from dawn to dark. Every ship under construction sang that song. How long did it take to caulk a ship? Months. A single caulker could seal 20 to 30 feet of seam per day. A 100-foot schooner had thousands of feet of seams, hull planking, deck planking, every joint. The work was slow, repetitive, brutal on the hands and ears. Caulkers developed distinctive calluses, thick pads on the palm where the mallet handle wore the skin, lumps on the fingers from gripping the irons, and almost all of them went deaf. The constant ringing destroyed hearing. By age 40, most caulkers couldn't hear normal conversation. By 50, they were completely deaf. But they kept working, because caulking was skilled labor, and skilled labor paid better. A caulker made $1.50 a day in 1930. A laborer made 80 cents. That 70-cent difference fed families. And if the caulker made a mistake, if one seam wasn't tight enough, the ship leaked, at sea, miles from shore, in a storm. Men pumped bilges by hand, trying to keep ahead of the water pouring in through a failed seam somewhere below the waterline. If they couldn't find the leak and recaulk it, if the sea was too rough, if the ship was taking on water faster than they could pump, the ship sank. Caulking failures killed ships and the men aboard them. So the caulkers took their time. They did it right, because a ship was only as strong as its weakest seam. Once the hull was planked and caulked, the deck went on. More planks, more caulking. Masts were stepped. Massive fir or spruce timbers fitted into the keel and rising 60 to 80 feet above the deck. Rigging was installed. Miles of rope, dozens of pulleys and blocks. The hull was painted. The bottom was coated with copper paint to prevent marine growth, barnacles, worms, algae that would slow the ship and rot the wood. Then came the test, launch day. The ship sat on building ways, wooden ramps leading down to the water. Workers greased the ways, knocked out the supports, and the ship slid down into the water for the first time. Would it float level? Would the caulking hold? Usually, but not always. Ships stuck on the ways, hung up halfway down. Ships hit the water crooked and had to be hauled back, adjusted, relaunched. And sometimes, rarely, but it happened, a ship hit the water and immediately started taking on water. The caulking had failed. The planking had split. Something was wrong. Those ships were hauled back out, torn apart, rebuilt. Months of work undone. But most of the time it worked. The ship floated. The crew boarded. The sails went up. And the ship that had started as a tree on a mountainside 2 years earlier sailed out into the Pacific, from stump to ship. 500 tons of timber, hand-cut, hand-hauled, hand-shaped. It worked. For 150 years, it worked. And then it stopped. When the old way died, there was no single disaster, no catastrophic failure that ended wooden shipbuilding. It died the way most industries die, killed by something faster, cheaper, better. The chainsaw arrived in the mid-1930s. Early models were heavy, unreliable, temperamental, but they were 3 times faster than a crosscut saw. By 1940, lightweight models were available. A single man with a chainsaw could do the work of a 2-man sawyer team. The first chainsaws weighed 50 pounds. You had to be strong just to carry one into the forest. They broke down constantly. The engines overheated, the chains snapped, the fuel lines clogged. But even with all the problems, they were still faster than a crosscut saw. By 1945, chainsaws weighed 30 pounds. By 1950, 20 pounds. The reliability improved, the cost dropped. Every logging operation started buying them. The crosscut saw died quietly. Mills stopped ordering them. Old sawyers retired and weren't replaced. Within 20 years, the misery whip was a museum piece. The men who'd spent their lives pulling saws found themselves obsolete. Some learned to run chainsaws. Others were too old, too broken, too set in their ways. They took other jobs, or didn't. Logging trucks arrived at the same time. Better roads, built by Depression-era WPA and CEC programs, made truck access possible. Logs that used to be dragged by horses and floated down rivers were now loaded onto trucks and driven to mills. Faster, year-round. No more waiting for spring melt. No more river drives. The first logging trucks were crude, converted flatbeds with makeshift log bunks, but they worked. A truck could haul 10 logs in one trip, a trip that took 20 minutes instead of 3 days. The math was obvious. The river pigs found other work, or didn't. The last major river drive in the Pacific Northwest happened in 1948. The river drivers showed up that spring like they had for decades. But this time, the company told them the logs were going by truck. No more drives, no more jobs. Some of those men had been driving logs for 30 years. It was the only thing they knew. They were 50, 60 years old. Too old to learn new trades, too broken to do heavy labor. They ended up on relief, or worse. At the sawmills, steam engines gave way to diesel and electric power, more efficient, safer. The old steam-powered circular saws were replaced by band saws, thinner blades, less waste, faster cuts. The steam engines were scrapped. The boilers were cut up for metal. The buildings were torn down. Within a decade, you couldn't find a steam-powered sawmill operating anywhere in America. And at the shipyards, steel killed wood. World War II was the turning point. The government needed ships, thousands of them, and needed them fast. Steel could be welded, mass-produced, standardized. Liberty ships rolled out of shipyards in weeks. Wooden ships took months. Steel ships lasted 40 to 60 years. Wooden ships lasted 15 to 30. Steel required less maintenance, smaller crews, handled heavy seas better. The math was obvious. By 1950, almost no one was building large wooden ships anymore. Fishing boats, yes. Small craft, where wood was still economical. But schooners, cargo vessels, anything over 80 feet? Steel. The shipwrights found other work, or retired. The knowledge went with them. The last wooden schooner built for commercial service in America was launched in 1954. A fishing boat out of Gloucester, Massachusetts, traditional construction. Keel, frames, planking, caulking, the whole process. The shipwright who built it was 72 years old. He'd learned the trade from his father, who'd learned it from his father. 3 generations of wooden shipbuilding. When he finished that schooner, he retired. Didn't take on another commission, didn't train an apprentice. The knowledge died with him. Today, there are maybe 50 to 100 men in America who can build a traditional wooden ship the old way. They're in their 60s and 70s. When they die, the knowledge dies with them. What remains, you can still see the remnants, The schooner Wawona sits in Seattle's northwest seaport, built in 1897, still afloat. The Charles W. Morgan, a whaling ship from 1841, is preserved at Mystic Seaport in Connecticut. Museums across the country hold the tools: adzes, broadaxes, caulking irons, crosscut saws. Walk through those museums, and you'll see the instruments of a dead trade. The axes with handles worn smooth by decades of use, the saws with hand-filed teeth, the caulking mallets with heads shaped by 1,000,000 strikes. A few wooden fishing boats still work Alaskan waters, built in the 1930s and 40s, continuously rebuilt, repaired, kept alive by crews who understand that wood flexes in ways steel doesn't, that a wooden boat is forgiving, self-healing, in ways metal can never be. But those boats are the last of their kind. When they're gone, that's it. What replaced the wooden ship industry? Fiberglass for small craft, aluminum for mid-size vessels, steel for everything big, faster to build, cheaper to maintain. No caulking, no rot, no termites, no constant vigilance against the sea's slow digestion of wood. You can build a fiberglass fishing boat in 6 weeks. No seasoning time, no searching for curved timber, no caulking. You lay up the hull in a mold, let it cure, pull it out, done. A steel trawler takes 3 months, welded construction, standardized parts, no wood rot, no marine borers. A steel hull can last 50 years with minimal maintenance. Progress. But what was lost? The connection between forest and ocean, the knowledge that a ship was a living thing, born from a tree, shaped by hand, kept alive by skill and constant care. The understanding that a hull's curve came from a tree's curve, that the ship remembered the forest. Steel doesn't remember anything. The last generation of men who turned stumps into ships is mostly gone now. The camps, the mills, the shipyards, abandoned or demolished. The forests have grown back or been logged again by machines. The rivers run clear, no more timber drives. You look at the Pacific Northwest today and see highways, cities, suburbs, but every bridge, every old building, every dock built before 1960, it came from those forests, cut by those men, hauled by those horses, shaped by those hands. The ships are mostly gone, sunk, scrapped, rotted away. But the timber they carried built the West. The fish they caught fed a nation. The trade routes they established connected isolated communities to the world. In 1930, there were 15,000 wooden vessels working American waters. By 1960, there were 500. By 1980, maybe 50. Today, a handful, museum pieces, curiosities, kept alive by enthusiasts and historians who understand what's being lost. They don't make them like that anymore. The ships, I mean, or the men.